reading just changed. Nobody touched the bridge at all. Same bridge, same morning. The reading shifted by nearly 20 meters. No earthquake, no construction. The steel is unchanged, but the numbers keep changing. A laser rangefinder targets Maine's Penobscot Narrows Bridge. Reading, 1,260 meters. Operator resets, 1,280, 20 meters, gone. The technician checks the battery, checks the lens, checks the alignment. Everything is normal. He runs the measurement again, a different number, again, different. A second device arrives, different brand, freshly calibrated that morning. They aim at the same anchor point. A different number comes back. Also wrong, 3 data sets on the table, 3 measurements, 3 different lengths, same bridge, same hour, same weather. Not one of them matches, not one. No repairs scheduled, no thermal event logged. Structural records show nothing unusual. By every physical indicator, this bridge is completely unchanged. Completely, provably unchanged. The numbers keep disagreeing, not by millimeters, the normal field error range, but by meters. 10 meters, 20. The gap will not close. The only variable nobody has checked is the observer. Who is measuring, how they are doing it, and what exactly they think they're measuring. But here's where logic breaks. If all 3 readings were correct, which number is the real length of this bridge? Pick one, anyone. Here's the surprising part. The answer is not a single number. It is a range. And that changes everything we knew about measurement. 2018, a Coast Guard team coordinates a barge passage under a Maryland drawbridge on the Chesapeake Bay. Clear skies, standard gear, routine. The vessel's GPS shows the bridge entrance 22 meters farther than the pilot's visual estimate. Both had been freshly calibrated that same morning. Both, today. The pilot trusted his eyes. The GPS disagreed. He slowed the barge, crept forward carefully. The 2 readings converged only when the vessel was underneath. No collision, no damage. The log read, positional data inconsistency, cause undetermined. The discrepancy was never formally investigated, filed away, quietly forgotten, still unexplained, 3 years earlier. Oregon, a survey team remeasures a highway overpass for a federal infrastructure audit. 2 engineers, top equipment, clear day, calm wind. Engineer 1, 614 meters. Engineer 2, at the far end, 626, 12 meters apart. Same bridge, same hour, same sky. They switched positions and measured again. The gap, 9 meters, but in the opposite direction. Neither result matched the other, or the original blueprints. Work was halted. A third team arrived the following week. Their reading, 619 meters. 3 teams, 3 different answers. 0 consensus, 0. The coordinator pulled historical records. Something odd surfaced immediately. This bridge had been officially measured 4 separate times since construction. 4 completely different values. Not within normal 1 to 2 meter tolerance. The full spread across all 4 official measurements, 17 meters. The project log was stamped, inconsistent spatial readings. Work suspended. Here's what made it worse. This was not unusual. Researchers examining long-span bridge records across America kept finding the same pattern. Bridge after bridge. Different years, different teams, different technology. Consistently inconsistent results. The problem was not the equipment. It was something nobody had a name for yet. So engineers did what engineers do when data refuses to cooperate. Escalate to GPS Geodesy, the most accurate large-scale positioning system ever built. The satellite reading came back different from all 3 previous results. Here's the part nobody expected. The satellite was not wrong. None of them were. To understand how that is possible, accept something uncomfortable. Measuring distance is not one thing. It is 3 completely different operations sharing one word. 3. Physical measurement. Tape, laser, total station. Geodetic measurement, GPS using a curved Earth model. Perceptual measurement, what your brain decides the distance is. Period. Each answers a different question. A tape follows the surface. GPS plots position in space. Your brain estimates crossing effort. 3 questions. 3 correct answers. In a short hallway, all 3 land on the same number. Stretch that hallway 600 meters over a river, and the 3 answers diverge. 2007. Virginia researchers asked participants to estimate a hill's steepness. Then participants strapped on heavy backpacks and estimated that same hill again. The hill had not moved. With the backpack, people rated it 10 to 15 degrees steeper. Same physical reality, different perceived reality every time. Distance works the same way. Tired, the path looks longer. Scared, it stretches. Energized, it compresses. Your brain is forecasting effort, not measuring meters. Now add the engineering layer. Steel expands with heat. A 200-meter span grows more than half a meter from cold morning to hot afternoon. On the George Washington Bridge, engineers log seasonal length variation near 1 full meter between winter and summer. It's designed for invisible to field measurements. A Washington state team placed a sensor at a suspension bridge midpoint. The sensor registered a span change. The anchor supports showed 0 displacement. 0. Inside the same crew, 3 specialists gave 3 explanations: coordinate reference drift, atmospheric refraction, thermal micromovement. Same raw data. All 3 were partially right. We are caught between explanations that cannot all be true, yet the data supports each one, partially. Not a solved problem, an active one. Theory 1, your brain, not broken, optimized for the wrong task. Action-based perception. Your brain predicts the effort cost of crossing, not the geometric distance. Cross a bridge rested and calm. Brain underestimates the length. Cross it exhausted or nervous. Brain inflates that distance. Same bridge, different forecast. That is not a flaw. For most of human history, knowing a route's effort cost mattered more than knowing its exact length. Survival over surveying. Theory 2, atmosphere. Air above open water bends laser light the same way a straw bends in a glass of water. Refraction, it compounds fast. Over 20 meters, bending is negligible. Over a 500-meter river span on a warm afternoon, refraction shifts a laser reading by several very real meters. Theory 3, mathematics. Benoit Mandelbrot formalized the coastline paradox in 1967. The finer your measurement tool, the longer any irregular boundary will appear. A bridge is not flat. Expansion joints, surface texture, tower shifts. A tape follows all of it. A laser cuts straight through. Different totals. Theory 4, coordinate systems disagree. GPS uses WGS-84, a mathematical sphere. A total station uses a local flat plane. A tape follows surface curvature. None of these methods is wrong. They answer different questions. How far through space is not the same as how much material spans this gap. Here is the uncomfortable truth. Every theory explains part of the 20-meter gap. Not one of them explains all of it. Something is still missing. But refraction and perception errors cannot make steel beams miss each other during construction. They cannot do that. And yet, that has actually happened. 1994. 2 prefabricated bridge sections came in from opposite ends. California, Sacramento River. Cable stayed. They did not meet. Gap, 1.4 meters. Official explanation, accumulated survey error. But every individual measurement had been verified. The failure wasn't one bad reading. It was the system losing shared reference. Researchers examining major American bridge records found the same pattern everywhere. Long-span structures had been remeasured multiple times. The values almost never matched, not once. The Verrazano Narrows Bridge has been officially measured repeatedly. Its recorded length varies by document. The spread across all published sources, 11 meters. Same bridge. Surveyors call this reference instability. No coordinate framework that all measurement systems agree on. Without that baseline, 2 perfect measurements of one object will diverge. 2011, Colorado. A maintenance worker crossed a footbridge that normally took 14 minutes at a normal walking pace. He knew this route well. He crossed it in 9 minutes. had not jogged, had not rushed. The bridge felt shorter. Supervisor logged it. A full survey was ordered, immediately. What had changed was the worker. He just finished a 12-hour shift. Fatigue usually inflates perceived distance. This time it compressed it. Nobody knows why. The data spread is enormous. People overestimate by 5 meters or by 25. The direction of error is somewhat predictable. The magnitude is never predictable. Modern bridge engineering has adapted. Major spans now include measurement, uncertainty ranges, deliberate buffers because no single field reading is considered fully authoritative anymore. One federal engineer, we stopped treating bridge length as a number. Now it's a confidence interval. The length is real. We just can't pin it. Here is the thought that rewires this. What if the bridge is fine, and our definition of a meter breaks down at this scale? Airport architects have known this for decades. A corridor's perceived length never matches its measured length, so they design to control how a walk feels. 3 expert groups, same bridge, 3 completely different verdicts. The geodesis, WGS-84, doesn't match local terrain. Error compounds across the full span length. Structural engineers. Methodology is the problem. Comparing tools never designed for direct comparison. It is like asking how many cups fit in a mile. Cognitive scientists. The observer is the problem. Human distance perception is an active construction shaped by fatigue, fear, and the effort your body predicts. What makes this unresolved? All 3 camps have peer-reviewed data behind them. No unified consensus paper exists. The scientific debate is formally and structurally open. 2019, an MIT team reviewed long-span measurement studies. Their conclusion, for outdoor structures over 100 meters, no single method is authoritative alone. That is a remarkable conclusion. We designed these to the millimeter. We poured concrete and drove steel, and still can't agree on their length. 2 people, same bridge, numbers almost 20 meters apart. You've seen the data. Honest answer, we know what creates the gap, not how it combines. Next time you cross a long bridge, your GPS gives one number, your eyes give another, your body calculates a third. None is lying. They are answering different questions about the same physical object. Not a flaw in the system showing you its true complexity. Finally, the bridge stands, fixed, certain. Touch the steel, count the bolts. By every physical measure, it is exactly and precisely what it appears to be. And yet the moment you step onto it, the bridge becomes something more. A measurement problem nobody has solved. A fixed object. Unfixed number. Different explanations exist. None is complete. Perception? Tool incompatibility? Math breaking at scale? What is your theory? Drop it in comments. I read everyone. We don't hand you answers here. We hand you sharper questions. Branding. Beyond Explain logo, like button, subscribe button. Keep asking. See you next time.